Okay, so I welcome you all to this session on problem solving and live interaction for the subject engineering mechanics. Before we start, I'd like to introduce myself to those who have not attended these sessions till now. My name is Ganesh Ramaswamy. I'm a PhD scholar working under the guidance of Professor K. Ramesh and co-guidance of Professor U. Saravanan from the Civil Engineering Department. And I'm working in the Department of Applied Mechanics at IIT Madras. So I welcome you all again. And just to brief as to what this session entails is we will be solving some problems from the course content pertinent to week 4. And midway we launch a quiz in the Google poll. On the right side you will be able to see an activities button which has a triangle, square and a circle. When you click on that you will be able to see that poll. We will have a question on the screen and then you can perhaps try answering whichever you think is the correct answer, just to keep it a little interactive. And based on the responses I get from the poll, if there is any lack of understanding or a clarity that is required, I will further explain that, just for me to gauge what is the level of understanding. And midway in between, if you have any questions, you are more than welcome to unmute and ask. And if it becomes too chaotic with more people unmuting, we can perhaps also use the chat box to answer. And before we begin, I'd like to emphasize that it will be better that you solve the question along with me, so that because I'll be solving it live, so it is better that in order to get a good understanding, you solve it along with me. And Swayam portal, there is an Ask a Question tab. If you click that, it'll take you to a Google forum, Google group basically, where you can also post your doubts, and we have been answering that, and many people get their doubts clarified there. Should you have a question, please feel free to ask there. And also, I would recommend that you join that Google group, so that even others, when they have a doubt and get it clarified, you get a summary, a digest of that, so it will be better for you. Okay, so with that, we'll start this session. Before we move on to week 4 content, which is beams, I'd like to make one small clarification, which was a question that was asked in the last session regarding zero force members. So basically, if we see how to identify zero force members, there are based on two conditions. If a joint that is free of any load has only two members connected to it, then both the members are carrying zero force, is one conclusion that we have seen. And the other conclusion is that if there be a joint where there are three members connected, out of which any two are parallel, then the force transmitted to the third member is zero. So the third member would be essentially a zero force member. So if we see, this question is what we had solved in the last class, and we initially said that joint D, we are able to see that it is free of load, and then ED and CD subsequently goes to zero because of the first condition. And then the remaining truss we had again solved, and in order to explain the method of sections, I had tried to calculate the force in member FE, which ultimately came out to be zero, which is when the student had asked the question, if we were to remove these two, now that they are zero force, if we are to remove these two, and then we again apply the zero force condition to the rest of the truss. By that logic, if we see this joint, we are able to see that there are no forces applied on it, and then it is connecting only two members. So these two also subsequently would be zero. To which I had prompted that this might not be a very sound way to do it, and we should take care of the original configuration in that is given. But I would like to qualify that statement a little, so that application of this is not wrong. It is correct to apply it this way, but I'd like to qualify it by showing you a common mistake that people do, so that you are careful of that mistake while you are doing this subsequently. That is, you are applying these conditions subsequently. For example, if we take the truss on the bottom right, this truss, if we take, so first, if we were to take this joint, let us say, so we are able to see that there are three members that are connected to that joint, out of which two are parallel. So we draw the conclusion that this is a zero force member. So that, so far so good. Now what we will do is, by that logic we will remove this member for the purpose of analysis alone. Now some students, what they do is they go to the same joint. Now they will reapply that condition that at this joint there are two members that are connected and this joint is free of any load. So by this first condition, naturally these two also must be 0. This is a condition that we need to take care about because this is a mistake. So this is what I meant by applying it once to the original configuration. Perhaps I should have qualified a little more, but nonetheless I am qualifying it now so that it becomes clear. So if we were to take this joint for example now, we have three members that are connected, out of which two are parallel. So subsequently this becomes 0. Once this is removed, for the purpose of analysis, we should not go back to the same joint and apply this condition again, saying that now there are only two members that are connected and we do not have any force. So these two will also be 0. This is an incorrect conclusion to draw. So the sum and substance of what we have discussed so far is that these are the two conditions that are required to analyze, to check if there are 0 force members. Since these are based on joints, so the best way to go about is at each joint you apply this condition only once. This will help you avoid all the mistakes that are possible. So by that logic, if you were to go to the original truss in question which was asked last week, we found out that these two are 0 force members because there is no force at D. So we have removed that, and subsequently we have removed that joint also. So we will not revisit joint D. We will not revisit this joint now since that has been removed. Even if that is not removed, as this was the case, this joint was not removed. Since we removed this member, it was still connecting two more members, so that joint was still in the remnant truss that you had. You are not supposed to apply that same 0 force condition again and conclude that the other members also are carrying 0 force. But if we were to take this, now that we have removed this, the remnant truss is this. Again, we apply to this joint. Since we are considering that joint afresh and this is the first time we are applying, it will not create any problems, and we can safely conclude that these two member forces are 0. Which in fact, if you remember, member in force Fe, even by method of section, it came out to be 0 towards the end, which was a ready conclusion that we could see, and even one student pointed it out. But I should have perhaps been more crisp in my explanation that why the subsequently applying could lead to errors, which I suppose that I have brought it out here clearly. So I hope this is clear now. So this is how we are supposed to proceed with identifying 0 force members, by making sure that we do not apply these conditions at the same joint more than once. Otherwise, going and trying these conditions out on the remaining part of the truss is fine as long as we take care of this condition. So this is something I just wanted to clarify ahead, so that people who perhaps see the last session alone don't get a wrong idea about what I actually meant. Okay, so if there are any questions regarding this, whatever aspect we have discussed, you can ask now. Otherwise, we will move on to the topic of discussion for today's session, that is beams from week 4. Okay, it is clear. All right. Okay, then we'll move on to this session about beams. So before that, I just need to introduce you to some small things. If we are given the axis like this, let us say xy axis, condition that is specified here is this is the positive axis that is given. So wherever x is pointing towards the right, x is taken to be positive, y towards the top is taken to be positive. If we were to draw the other ones, these are the directions representing the negative axis. So this is so far for the coordinate system. And if we are to cut a section somewhere, and then so when we cut a section, this has divided the beam into two segments. One segment is like this, and then the other segment is like this. So we see from the coordinate system that is given for this question, this is the outward normal to that section. And if we were to consider the right section, this is the outward normal, the normal that projects out of the surface. if the outward normal coincides with the positive direction of our coordinate system, that surface is called a positive surface. If the outward normal coincides with the negative direction of our coordinate system, it is qualified as a negative surface. So by that logic, if we see, this is a positive surface we have identified. And the other one that I had drawn, the right side portion, it has a normal that is pointing in the minus x direction, so it is a negative surface. As for this sign convention, this is invariably to be read in conjunction with our coordinate system that is given. So the implication of this is, what we are trying to say here is, according to our coordinate system, the positive surface, that is this is the positive surface. On the positive surface, the forces, the shear forces that point in this direction are taken to be positive, and on the negative surface, the shear forces directed in this direction are taken to be positive. That is how this is to be read, which will become more clear when we develop the bending moment diagram and shear force diagram. But this is something I just wanted to clarify outright, so that you have some kind of context when we actually talk about these things. Okay, with that, I think we can start solving this. The question here is, consider a simply supported beam with the positive coordinate directions given. These are the positive coordinate directions that are given. Even if this was not mentioned, even if only the axis is given, we are supposed to take it that that is the positive coordinate direction. And the applied loads are shown along with the sign conventions to be used. Okay. So first we have to find out the vertical reaction at support A, the vertical reaction at support B, and then the task is to develop the bending moment diagram and shear force diagram for this beam. So let us proceed to do that. For simplicity's sake, I draw this as a line diagram, and then we know that this is a hinged joint. So this basically has two restraints. It arrests translation in both directions. And B is a roller joint, so we have discussed this in length, that it offers only a vertical restraint. And then we have a load here which is 25 kilonewton that is given. Then there is point C where a couple is applied, which is of magnitude 12 kilonewton meter in the clockwise direction, and we qualify this as point C. This is point B, this is point A. Let us call this AY, at support A pointing in the y direction. Let us call this reaction AX, and let us call this BY. And then in addition to this, at point A we have another couple that is applied, which is 15 kilonewton meter. Okay, now that we have drawn the free body, that is, we have isolated the supports and replaced them with the forces, reaction forces that exist, we have the free body diagram of the beam that is ready. Now our job is to first calculate what are these unknown reactions AY, AX and BY. We can see that this beam is in static equilibrium. So we have three planar equilibrium equations at our disposal. Let us apply them subsequently as we did for the truss in order to calculate the reaction forces. So we know that there is no acceleration in the x direction. So sum of all the forces in the x direction sum to 0. What are those? Minus AX, because it is pointing in the minus x direction. Are there any other horizontal forces that are applied? No. So this equals 0, which gives us AX is equal to 0. Many might be able to recognize this upfront by looking at the beam, but for the sake of completeness, for those who might not understand this outright, I am just explaining this so that it becomes easier for you to solve the questions. Now sigma Fy equals 0. What will this give us? AY plus BY. Both are the forces, reaction forces at A and B pointing in the upward direction. Do we have any other force that is applied? We have a force applied at point B, which is pointing in the negative y direction. Do we have any other force that we have not accounted for? We should be careful that these 12 kilonewton, 15 kilonewton meter, 12 kilonewton meter and 15 kilonewton meter, they are not forces, they are couples. They are not, the two are very distinct things. So we should not account them while summing up the forces. So this equals 0, from where we get ay plus by equals 25. This is one equation that we have got. Okay. Now the third equation at our disposal is that summation of moment about any point in space is summing up to 0. So we can take moment about any point and it would sum up to 0. But for convenience sake, in order to eliminate the unknowns, the general practice is that we take the moment about either one of the supports, so that the contribution of the moment due to the reaction applied at that support becomes 0, because moment is r cross f. If we were to take moment about B, then By's contribution would be 0 because it passes through B. So r is essentially 0. R cross f also becomes 0. So if we were to take, let us say, take the moment at B. Now Ax, if we can use the principle of transmissibility and we can transfer it to B, that also passes through B. So Ax also has no contribution. So Ax into 0. And then we have minus Ay into 12.75. I'd rather use bracket so that it is not confused with a cross product, into 12.75. Why this is negative? Because this is clockwise, as we had discussed last time. And then what else is there? We have 15 kilonewton meter, which is also clockwise. And then we have 12 kilonewton meter at C, which is also clockwise. And do we have any contribution from this 25 kilonewton force or By at when we are taking moment at B? It would be 0. So I'll just write it out like this. I'll just write it out for the sake of understanding. So that it becomes clear for anybody who sees this later. So with this, we have only one unknown in this equation. So we can actually calculate what By comes out to be. So that will be, that comes out to be minus 2.12 kilonewton. So minus implying that whatever direction we had taken should actually be downward, because this beam is lifting from there. So at A, the hinge is pulling it downwards. That is all it means. So subsequently By we can calculate from this equation we have. Ay plus By is 25. So this will be 27.12 kilonewton. So far so good. Now we are supposed to draw the shear force diagram and bending moment. Yes. You have any question, Amarnath? Yeah, we can take. Okay. In order to get that also. Okay, I will solve it by taking about A also. Okay. So the question. Yeah. So we'll just consider this again. Okay. So the question was whether we can take a moment about A and solve instead. So why not do that also and convince ourselves that what we are doing is correct. Okay. So point A, summation of moment about point A equals 0. So we can see that By will create a anti-clockwise moment, which is to be considered as positive. Anything else? So minus 25, that is applied at B, that is also 12.75. Since at C we have a clockwise couple applied, so this will be minus 12. Similarly, at A we have a minus 15 kilonewton meter clockwise couple applied. And by similar logic, we can see that Ax and Ay will not contribute. So I am just sparing you by not writing it here, but you can figure out that Ax and Ay, since they are applied at A, they are not contributing to anything. This comes out to be 0. Now the thing is, it should add up. So if we see By into 12.75 minus 12 minus 15 equals 0. So we get By coming out to be 27.12 kilonewton if we solve this, which is identically same as what we were getting earlier. Now we know that Ay plus By equals 25 from the from this equation which we had derived, sigma Fy equal to 0. So naturally, if we substitute this, we will get Ay as minus 2.11 kilonewton. So we have seen that no matter which point we take, the reactions come out to be the same. So that was a good question. So that this gets so that you get clarity on this. No matter how we solve, it will come out to be the same. I hope you are convinced now. Okay. So to draw the shear force diagram and bending moment diagram, first we should identify some key points. What are those key points? In a beam, there are some key points, let us say. Key points are supports, then load points. That is wherever there is a load or wherever a distributed load ends, all these points we should identify and mark them. Where geometry changes, although we don't essentially deal with the beams in this course where there will be a sudden jump in the geometry, but nonetheless those points also we should consider. Even if you don't come across it now, you might come across it later, so you must be comfortable with drawing the bending moment diagram. Load points also include couple points where couples are applied. So in our beam, if we were to take this is our beam. So we can identify that there are, let us extend this, we can identify that there are three key points. One is two happen to be the support themselves and one where a couple is applied. Okay, so this will make our job easier. Now first, the key points why we identify is because we want to split the beam there. Split the beam and analyze the things individually. So now we will split the beam into two, and then first we will develop for AC. Section AC alone we will analyze for getting the shear force variation, for getting the bending moment variation. Then we will analyze section CB. This is the idea behind getting the key points. Okay, now if I were to take section AB, and then for the sake of convenience, I drew it as a line diagram, but actually if you see section AB, AC is like this, where this is point C, where a couple is applied, 12 kilonewton meter. And then we have A, where a force of minus 2.11 is applied. Minus because I had initially taken that direction, so I'm not changing it. AX came out to be 0. Is there anything applied? There is a moment applied. 15 kilonewton meter. Okay. Now I'll just use this a little bit because I want to explain something there. So if I move it here, it is applied at C. Now at this section C, from the section we have cut, we can see that it is a positive surface because the outward normal is going in the positive x direction. If we see, this is the positive x direction. At C we will have an outward normal going like that if we cut and take the left side portion. So that's a positive surface. And what does our sign convention say? Our sign convention says that positive surface, we have to mark positive shear as downwards. So we will mark a shear force there pointing down. This is V at section C. And then similarly, what does our moment moment convention say? That at a positive surface you mark anti-clockwise moments to be positive. So we will mark an anti-clockwise moment here and take it as MC, moment at C, bending moment at C. Now we have completed this diagram. Now what are we to calculate? We just have to calculate VC and MC. Now that we have applied the sign convention once, our job becomes easier. We just need to calculate what is VC and MC. Similarly, as we did for the reactions, we just need to apply the equilibrium conditions again. So I'll just copy this once. if I were to paste it here. Okay, so summation of fx of this free body equals 0, because if the total system is in equilibrium, even a part of it will be in equilibrium. That is what we saw in week 2. Even the subsystem has to be in equilibrium. So we have minus 2.11. Is there any other force that is applied? Mind you that 15 kilonewton meter and 12 kilonewton meter are couples, they are not forces. Is there anything else that we have not accounted for? VC we have not accounted. So it will be VC is pointing downwards, minus VC equals 0. So VC comes out to be minus 2.11 kilonewton at C. With this, can we develop the bending moment, the shear force diagram? We could, but why not consider the other part also and do the study fully? Similarly, MC we have not yet calculated. Let us calculate that also. Moment about any point. Again, if we conclusively saw that irrespective of which point we take, the reactions come out to be the same. By similar arguments, we can say that irrespective of where we calculate the moments here, MC's value will not change. So, if we were to consider it at C itself, the right end itself, VC's contribution gets cancelled. It doesn't come into the picture. So, why don't we consider it there? Okay. In that case, we can see that we will take this at C, sigma moment at C equals 0. So we will see that minus 2.11 makes a clockwise moment, which is negative. At C, what is the distance to this thing at C? If we see, this is 4.4 meters from the question. So this length is actually 4.4 meters. Right. So this will be 4.4, but this moment will actually be, if I were to correct the sign, this thing will be pointing downwards. So it will actually create a clockwise, anti-clockwise moment, which is actually positive. That is why we have taken this to be positive. What else is there? Then we have a clockwise moment that is minus 15. Then we have another clockwise moment applied at C, that is minus 12. Do we have anything else that we have not accounted for? VC, its contribution is 0 because we are taking moment at C only. And then we have MC. MC is applied in the anti-clockwise direction, which is positive, equals 0. So what does MC come out to be from here? It comes out to be 17.716. Yeah, kilonewton meter. Okay. Now let us consider the other portion. We have done it for MC, for AC. If we were to do it for CB now, CB we can similarly draw. Sorry, this is the other question that we had. CB, I'll just try to squeeze it here so that so we have, I'll correct it this time by pointing it 2.11 downwards, because here I have made it pointing upwards and written minus 2.11. I have just reversed and skipped the minus because I have already reversed. I hope that is clear. There is no confusion in that regard. Then we have 15 kilonewton meter applied. Then at C we have 12 kilonewton meter applied. Is there anything else that we have missed? This is at some section X. Some section which is at distance X. It is at this X we are cutting the beam. So no other forces applied over there, except we just need to account for the shear force and bending moment at that section. By similar logic, we can see that this is also a positive surface. So according to our sign convention, our shear will be pointing downwards, positive shear, and then our moment will be like this. Now we just have to calculate, by similar logic, we have to calculate this is moment at that section X. So this is going to be a little interesting because it will give a moment equation which is a function of x. First, let us calculate the forces. Summation of Fy equals 0 gives us minus 2.11 because this is pointing downward in the minus y direction. Anything else? Minus Vy. We have accounted for everything, all the forces that were applied, equals 0. So this again gives us minus 2.11 at any section, kilonewton. Which is, if you note, it is the same shear force that we got for the other section also. What it is telling us is that shear force is constant throughout the beam. It doesn't depend on x. Wherever you take x, it still remains same. So moment, let us consider moment at the right end again. Moment at section x. At this section x, sorry, I'll just write it a little neatly. Summation of moment at this section x, if we were to say. So now this 2.11 equals 0 would give us 2.11 into x, because it is creating a anti-clockwise moment. I have taken it as positive, 2.11 into x, minus 15 minus 12 plus mc, and vy's contribution being 0, I am not writing it, so that is to be understood. So mc comes out as minus 2.11 x plus 27. Okay, so we have got an equation for mc now. If we were to substitute x equal to, what is x? What is the domain of x here? We are considering the section. We are considering the section CB. For AC, domain of x is 0 to x to 4.4. For CB, domain of x is 4.4 to x to, what is the total length? 12.75. So this is what we are supposed to take as the domain. So if we were to apply this at 4.4, what will be mc if x is equal to 4.4? We will get 17.716, which is same as the moment we got from the analysis here also, if we were to just calculate that. And towards the end, if we have to apply minus 2.11 into 12.75 plus 27, it comes out to be 0. It will come out to be 0. You might get some small value because we have rounded this off. This should actually be 2.11 followed by some numbers. So what this is telling us is at the hinge joint, moment should be 0. That is the essence. So with this background, can we now draw the shear force diagram and bending moment diagram for this? We know for the whole beam that shear force came out to be, for AC section, shear force came out to be minus 2.11. For CB section also, shear force came out to be minus 2.11. So it is just a rectangle minus, and this height is 2.11. It is in the negative direction. Now, if we have to consider at at C, the moment at B it is 15. So it comes down like that. And then we add up 12 and this thing, it will add up and it will go to 17. If you were to consider it like this. So here, what will this magnitude be? It will be by minus 25, which is 27.11 minus 25, 2.11 into 12.75 minus 4.4, which comes out to 17, which is what we had got from here, 17.716. 716. Now this moment was anti-clockwise, but we can see that at C there is a couple applied, so there will be a jump in the bending moment diagram. It will go down by 12. So this remaining will be 5.711, and then it will pick up again, go to 15, and then come back to 0. So this is the bending moment diagram for this question. So we have successfully plotted the shear force diagram and bending moment diagram for this question. So if there are any doubts in this, I would encourage you ask now. So before we move on to the next question, please feel free to ask any doubts if there are any. Yes. Yeah. Good evening. Yes. Yes. See, it is actually even in. Okay, I'll answer your question. Uh, if we see here, the the question is that why we are taking this as positive. Uh, that is, if we have it like this, positive shear, why only downward is on the positive surface is positive and why not upward? It's a matter of convenience, that's all. Actually, in the initial days, as professor also mentions in the lecture, what happened was there were many authors that were writing books. So in order to avoid this copyright issue, it seems that they had developed different conventions, but ultimately it is representing the same thing. So even if you go, this is what is given in Miriam. In the book Miriam, which we are following for this course, this is the sign convention that is given for the shear force. Whereas if you go to higher studies, that is strength of materials and higher courses, if you see books like Crandall and Dahl, so that there the shear force convention will be opposite to what was considered here, which is the reason why the professor has discussed both these sign conventions in detail. The idea is that if there is a beam and if you are given a sign convention, you must be able to develop the shear force diagram according to that sign convention. That is the idea. So see, shear force convention, it is, that is, we are doing it for the sake of understanding. That should not in any way change the physics of the problem, because we all are open to interpretation and we may develop our own conventions, but ultimately the physics should add up, which it would. If you see, if you solve the question with both these, this thing, the value will still come out to be the same. Only difference is that shear force will be the exact mirror image about the x-axis for these, but interpretation still remains the same. I hope that is clear. Yeah. Yes. Positive. Yes. 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 Okay. So the question is that, yeah, yeah. I think I understand what you mean. I'll complete my explanation and then if there are any remaining doubts, you please ask. So the question is, generally, if we consider an XYZ coordinate system, the Z will point outward because of the right hand rule. So any moment that is taken anti-clockwise is considered to be positive because its axis will align with our moment's axis. That is why anti-clockwise moments are taken to be positive, clockwise moments are taken to be negative. Whereas when we come to this sign convention, on this surface we have been given this is positive, on this surface we have been given this is positive. It is to be clearly understood that whatever is given here, the sign convention that is given here, is the internal response. It is not the actual moment that is being applied. There is a difference between the two, which I'd like to clarify. Just a moment. I'd like to perhaps clarify. Because of lack of space, I'll just clarify it here. So the idea is that one is called a bending moment. For which sign conventions are given. Like this. What this tells us is when we take a section, depending on the surface, we just have to apply this bending moment. Once we have applied this bending moment at that free body, it becomes a externally applied moment. Then we are supposed to treat it as an externally applied moment. And for externally applied moments, we have the sign convention based on our coordinate system. Z, X, Y. all clockwise, all anti-clockwise positive, clockwise negative. So the idea is this is an internal response. So if we take a beam, let us say this is a beam, and then we identify the surface which is a positive surface, we simply, because we have cut the beam here, this is a section of the beam which we have taken, we need to account for whatever was the internal moment there, internal bending moment there. For this we refer this sign convention. What it tells us, if this is a positive surface, you just apply the moment in this direction. So we apply the moment in this direction. We name that moment for convenience something. If we have taken this x section, we name that as mx. That is all. Now that this has been applied, now that this has been applied, sorry, once this is applied, this is to be treated as externally applied system. So this entire thing will now be in equilibrium. External system. This entire thing will be in equilibrium, which means while adding up, this mx shows up as an externally applied moment. We know the convention for externally applied moment. As per our this thing, we can see that anti-clockwise moments are positive. So mx will be adding up as positive. This is the idea behind that. Does that answer you, Kannan, or if you have any remaining doubts, you please ask. Okay. Shear. Yes. Yes. Yeah. Okay. Okay, okay. I understood the question. So I got it. So the question was that if we consider this box as part of the beam, then what this shows is that both these forces rotate it in the clockwise direction. So that is a very valid doubt. Only thing we must remember is that you also take note of this, that sign conventions shown are at a section. What this means is, this box which you see, it is not a part of a beam. Actually, in a beam, this is a beam. There is some load applied, let us say, and then there is some support condition, let us say. From this, we will take one section, and at that section we have a point. This point we will represent by a square, because at that point, if you look from the left side portion, from this left side portion, let us say this is portion 1, portion 2. From portion 1, if you sit and look at that point, the outward normal would appear to go like that. If you look at the same point, sit in section 2, the outward normal would look like going this way. So it is a representation of a point. Of a point of 0 dimension. This is not to be considered as part of the beam. This is to be considered at a point. It is just a convenient way to represent two surfaces. So if they could have drawn two diagrams saying that if the normal is pointing this way to the right, then you take shear force of that. If the normal is pointing to the left, you take shear force of that. Because both are possible at a point depending on which is your vantage point. Whether you are seeing it as from portion 1 or from 2, these two will differ. They have just condensed it into one single square. That square is not part of the beam, but it is a representation of a point. Okay, I hope that clarified your question. Okay, thank you, thank you. Good, some good questions have come up today. Are there any other questions that we can take up, or if not, we will move on to the next question that was there to solve. Okay, in that case, I'll just show. Based on what we discussed so far, it's an interesting question. So we have got the options there. I'll just launch one Google poll so that we just know we just try to understand what it is. And there could be more than one option correct for this. So whichever you think is correct, any one of them you can select, no problem. Because the idea is that I just want to see how far what I have explained has sunk in. So the poll is active. You can just see it on the right side of your screen. And the question is over here. Which of the following options, there could be more than one, describes the sign convention adopted based on the depictions of positive shear force on the free body shown. So we have a beam. Okay, we have cut a section out of that. And this is our positive coordinate system that is given here. That is rightward x is positive, upward y is positive. And on that surface, we have applied shear force. What is given is depiction of positive shear force. It is already given that at these surfaces, positive shear force has been applied according to some convention. We have to find out what that convention was. And then at this surface, this is the shear force that has been applied. Here, this is the shear force that has been applied. So the answers given are positive direction on the positive surface indicates a negative shear force. Positive direction on positive surface indicates a positive shear force. Positive direction on a negative surface indicates a positive shear force. And then negative direction on a negative surface indicates a negative shear force. B. Okay. If there are any other answers, you please log them there in the poll, and then I will explain this question in detail as to what this was. We have had some answers now. Okay, so I'll end this poll as of now. So people have answered A and B. This is what the answers we have got. So let us see which one is actually correct. So positive direction and negative direction. What does these things imply? These imply y. Positive direction means y, force pointing upward, because that is what our coordinate system says. Negative direction means this, negative. On a positive surface. Which is the positive surface here? If let us say I erase this, I call this figure 1 and I call this figure 2. Both are representing free body of the beam, two different free bodies of the beam. Out of these, which figure represents a positive surface? For this surface, outer normal is like that. For this surface, outer normal is like this. Which would represent the positive surface? This outer normal coincides with the positive x direction. So this is the positive surface. Subsequently, this is the negative surface. Okay, we have identified which are the surfaces. So in the question, it has been given that positive shear force were depicted. In now positive direction, first option, positive direction in the positive surface. Positive surface meaning figure 1. In figure 1, positive direction, does that indicate a negative shear force? Question says that it is positive. So A is not the correct answer. Positive direction on a positive surface indicates a positive shear force. It is given that positive shear force was applied on a positive surface in the positive direction. So B is correct. Let us say C, positive direction on a negative surface. This is the negative surface. Positive direction is upward, indicates a positive shear force. We have been shown something and we have been told that it represents positive shear. So this cannot represent that, which is why C is not the correct answer. Subsequently, D would become the correct answer because it's just the complement of that. So B and D represent the correct answer. So if we were to contain all this, see, if as somebody had asked, if this was the question that was to be asked, and in each and every question, if we were to give you these two big statements which are correct, B and D, it would be very confusing what to identify how, which is why we have condensed it into a small representation to be read in conjunction with our coordinate directions x and y. How this is to be read? Positive surface. This is the positive surface. Our right side surface is positive because it has outer normal going like that, outward in the positive x direction. We are just saying on the positive surface, you mark a force that is pointing upward and call it positive shear force. On the negative surface, similarly, that is you mark a force that is pointing downward and consider it to be a positive shear force. This is the interpretation. This is why we have come up with this condensed representation of a shear force diagram convention, sign convention, so that will these sessions be available on NPTEL? Yes, it will be available. We will. I am also recording this session, so it will be available sooner or later. We will be uploading that. And also this sheet which I'm working, this PDF where I'm working out the problem, this also, these slides also will be made available. So should there be any questions later, at a later stage also, you can ask in the subsequent live sessions or you can ask in the portal. I hope that is clear. So this is why we contain shear force diagrams convention into a small compact notation like this, so that we can avoid mentioning these big statements. I hope this has become clear now. So the correct answers were B and D. For those who think that this is very formidable and they are finding it tough, you just consider this question which we had solved. You try to solve it on your own based on this convention that was given. And if you are not getting the correct answers, feel free to reach out to us anytime and we will clarify it. Either on the forum, you can also work this out and ask in the next session. Every Friday we will be having this session at 6 o'clock, 6 to 7. So whatever your questions you have, please feel free to bring them up so that it becomes clear. In fact, I wanted to solve one more question today, which was this one. But anyway, I don't know if we have the time to do that. But anyway, let us start. And should we get, we will just identify the key features of this problem. And then if there are any questions, you please ask. So consider a simply supported beam loaded as shown, along with the sign convention to be adopted. Sign convention is given as usual here. Positive coordinate directions are given here. And then we have been given a simply supported beam with some load, generic load that are applied. First, what are the key points if we were to calculate, if we were to find them out? Key points, one is A, because one is B, represent the supports. Okay, what else? We have a load that ends at D, a uniformly distributed load that ends at D. So D becomes a key point. C also becomes a key point because a load is applied at C. Then E also becomes a key point. Are there any other points to care about much? Because others have continuous systems that are going in. Geometry is similar, load is also similar, like that. So we have abrupt changes only at these 5 key points, namely A, B, C, D and E. Why we do this is because we want to identify where to expect the jumps in the shear force diagram and bending moment diagrams. So we can expect jumps at these points. Okay. Now first step of business will be to calculate the reactions as usual. So let us just calculate it. I'll do it a little fast so that we are able to solve something today. I'll represent this by AY. I'll represent this by AX. And I have a force here BY, upward force BY. Okay. Now if we were to take sigma Fx equal to 0, Ax comes out to be 0. So I won't solve it because we can see that that is the only horizontal force that is applied. Sigma Fy equals 0 gives us Ay plus By equals what? 2 kilonewton this thing. Then we are supposed to account for 2 into 4, 2 into this length 4, because that is the total force that is applied, plus 1 into 4. So Ay plus By comes out to be 2 plus 8 plus 4, 14. Now I will directly write the equation of ay by taking moment at b. So if you want, you can write with me in order to get it clear. So it will be minus ay into 10 plus 1 into 4 into what will be that distance. 1 into 4 is a force applied here at the center of 4. So this is 2 meters. What will the rest of the distance be? It will be 8. Okay. And then we have plus 2 into 5 plus 2 into 4 into 4 by 2 equals 0. So ay would come out to be, it comes out as 5.8 Newton, kilonewton, sorry. So by will come from there we can see that it will come out to be 8.2. 14 minus 5.8 is 8.2 kilonewton. So one thing we are sure of is at B, if we were to consider at B, we slice this beam like that, and then we consider positive the left side portion. We have a positive surface. At positive surface, By is acting. By is acting upwards, which is negative. So we have a shear force directly coming out to be negative 8.2. At E, if we were to calculate, it will be 8.2 minus 8, which will come to 0.2. So it will be coming like this. This is a straight line. Then there will be no change till here. Then we have a jump in the shear force diagram because a point load is applied. It will go like that. Then we again have it constant. Then it will increase like this. 8.2, 5.8, sorry, it will come like that. Yes, it will increase like this. This will be 5.8. Ultimately, it will add up. This is 0.2. So 0. Minus 0.2 plus 2, it is 1.8. 1.8 plus 4 is 5.8. Here also it will be 1.8. This is positive shear force, negative shear force. So for many might be thinking how this has been drawn so quickly. I would suggest what you do is you consider this section first, section AD, then section DC, then CE, then ED. For these 4 sections, you have to draw the whatever we did earlier. No? We have split the beam and then we put the shear appropriately, and then we calculated shear force at every section. I'm just giving you the result outright because we are running a little short of time. But I would encourage you to solve this question on your own, and then if there are any doubts, come to ask it in the next session or in the forum, however it is. Similarly, bending moment diagram also one should draw. I would rather recommend that you try it out on your own. It will come out something like that. It will be straight, and from here it will be a parabola. So it will be totally positive. I would encourage that you try it out once. I'll just give you the values here. What this value will be? It will be 15.2. Then from the left side it will be 16.8. This will be 16.8, and at the center it will be 5. It should be 17. That is what it comes out to be. So I would encourage all of you to try this out once and then come up with your questions. But in the meantime, if whatever, based on whatever we have discussed, if there are any doubts, I'm more than happy to answer them and take the questions. So everything is clear. That is basically what we need to do in this question is we take this as a section, then we have a section at x. We cut some section at distance x. So first x will vary from, for AD, x will vary from 0 to 4. Then for DC, x will vary from 4 to 5. Like that we'll go. CE, x will vary from 5 to 6. And then from for EB, x will vary from 6 to 10. Like this, you will get 4 or 5 equations based on which you will be able to get. So the general way is to first identify the key points, and then at those key points you identify you calculate what is the bending moment, what is the shear force. Then based on our knowledge of the load and of the shear force diagram, we can easily connect the dots, whether it will be a straight line connecting it or whether it will be a higher order curve connecting it. We'll be able to see that. Okay, there is a question, sir. Please suggest some books for this subject for competitive exams like GATE. Actually, the book Miriam has quite a lot of examples and exercises to solve. So I would suggest you go with Miriam. And if you are not aware, there is also a GATE portal now created by NPTEL. So there are many previous year questions that are being solved by many of the students and uploaded there. So you can also visit that. In addition to the lectures, you can just consider watching the lectures, and you can try out questions from Miriam, and should there be any doubts there, to ask them in the forum or perhaps in the live sessions. But I would suggest that you keep it to that particular week. For example, next week we are going to be solving questions from virtual work and energy principles. So if you have solved any question there and then you have faced some issue, I would suggest you bring that up, and we can together we'll find where the problem lies if you didn't get it correctly. I hope I've answered your question. Is there anything else? Any other questions that are there? Okay, thank you. And are there any other questions anyone else has about what we have discussed? Positive surface, negative surface, these things are clear. How to draw the shear force diagram, bending moment diagram. This takes a little bit of practice, because outright if we see a diagram that is being drawn straight, it might look a little formidable, but I have also solved one question fully explaining how it is to be done. Get more practice, take some couple of, there are many examples like this. Take a couple of examples and try to draw it on your own, and then perhaps if there are any doubts you ask to get it clarified. It is not that tough a concept. Only the sign convention is the thing that generally leads to confusion in students. But I hope that I have been able to uh, do some justice to it by explaining what it meant. So if there are any other questions in this regard, I'll be happy to take them now. Lectures and weekly session help a lot for building. Okay, only for additional problems. Building concepts only for additional problems. Yes, that's good if they are helping out. Anyway, that is the main motive of this initiative, that the assistance that is required for students to understand the concept is given on all scales. So if that is working out, we are happy that it is working out. And if you have any suggestions to improve these sessions also, you're welcome to share them here so that we can incorporate. Of course, it's a process that is going on. So this process can always be improved with your feedback. After all, it is for the benefit of the student. So I encourage you all to give your feedback as well in this regard. And thank you for that feedback. Anything else other than this explanation is good. Thank you. Okay, I take it that there are no more doubts, at least for now. So if that be the case, then I will consider ending this session here. On this note, that I would suggest you please solve these questions. If you are someone who you're working for grades, or this is part of your course, then I would highly recommend that you solve a couple of examples and get your doubts clarified, because the sign conventions can sometimes be a little confusing. But once you get the hang of it, nothing is more scoring than trusses and beams. So it is the most scoring of the entire portion of engineering mechanics, if you ask me. So it is very essential that you understand this correctly. Thank you very much. Okay. Okay. On that note, I suppose we could consider ending this session, and so I'll see you in the next session. I hope you will join next Friday at 6 o'clock, so that we can discuss problems on virtual work and any remaining doubts that you have on beams or trusses also. Okay. Thank you.